Okay, the last of the word problems that involve derivatives. Most of you guys, like optimization problems better than related rates because optimization problems don't require any implicit differentiation. So the differentiation is the easier part when it comes to these word problems. What might be a little bit harder is setting it up and coming up with the equations because you need 2 and sometimes 3. So that's the difference in this. So hopefully you watched the video. Dr. Taylor went through the first one, which, by the way, well, he did some basic ones. But the first real word problem he did, this fencing problem, if you looked at the old exams, there's a lot of the optimization problems revolve around this kind of a problem. Now, I'm not saying that that's what you'll see this time, because every time I say that, it won't show up. But this is a very common one, so you can at least plan on it on your test, okay? All right, so he did those with you, so we're going to start. What I did on our notes is, again, I always try to give you guys steps. Some of you like it, some of you don't. But this is just kind of a way for you to remember what you're doing when you see an optimization problem. You're not going to see the word optimize, by the way, okay? You know, when you did a related rate problem, it always said find the rate, so you kind of knew that was a related rate problem. These don't really say optimize, okay? This will say things like find the maximum value, or find the closest point, or find the smallest something, okay? So you're not going to have a word that says optimize this problem. Okay, so that's the one thing you have to be very careful that you understand that's optimization when it's asking you to find largest, smallest, closest, things like that, those words. Maximum. I'm going to lose my voice already. I just started. All right. So, first thing, always, read the problem. Okay. Most of these have a picture that come with them, but if not, you would draw a picture. And then it says come up with the objective equation. Dr. Taylor calls them objective equations. That is the main equation that you're going to try to optimize. So usually in my lingo, I say main equation, because to me that makes more sense. You have a main equation, and then you have the other equations, which I call secondary. Okay? So in the video, Dr. Taylor calls the main equation the objective, and then he calls the secondary equations are the constraints. So that's fine if that's the way you've learned them and you're okay with that. So I just highlighted my words because I usually will say the main or the secondary. It just makes more sense to me because the main equation is the one that I'm going to be working with most of the time. All right, so you got to come up with your main equation. You have to come up with the constraints or the secondary equations, which could be more than one. You might have more than one, which is actually the first number 4 that we're going to do. We'll see that. Okay. Then the bulk of this is that you're going to solve the secondary, your constraints, for one of the variables, and then you're going to replace that equation, that part of the equation, into the main equation. So your whole idea, before you start taking a derivative, is that your main or your objective equation must only have one variable in it. Okay? So no implicit differentiation, which is kind of nice. After you do that and you simplify, then you'll take your derivative. And from there on, it's usually pretty easy. If you can get to the derivative part, you are good, okay? So we're going to go through all the different kinds of these, just like we did with related rates. You have several pages, and I know I probably won't get to them, but you have several good pages of optimization problems in the appendix. I am going to post all of those answers worked out. Those are old, I think every one of those are old exam problems. So there's a good place for you to practice some of those and have that answers. So make sure you spend some time and look at those appendix pages, okay? All right, so let's look at number 4. And then we got a few more of these to do today, and we'll hopefully by the end kind of feel a little better about these. All right, so number 4 says you have a box that you're going to make out of a 10-inch by 18-inch piece of cardboard. You're going to cut squares out of each corner, okay, so that you can fold this box or fold the cardboard and make a box. Okay, and the question says find the length, the width, and the height of the resulting box that'll maximize the volume. Okay, so again, the first thing you're going to do when you look at a problem is figure out what you're trying to optimize. So I want to underline where it says we want to maximize the volume. Okay, maximize, that's an optimization word. Okay, so that's the only way you got to know is by looking at these words. All right, so that means that we're going to have our main objective equation that we want to solve will be the volume of a box. Okay, so we're going to come up with our main equation, and this is why I don't write the words objective and constraint. I do main and secondary. Okay, all right, so your main equation is going to be the volume. So the volume of any three-dimensional prism, length times width times height, right? All right, so basically what we're trying to do is we've got a piece of cardboard 10 inches by 18 inches, and I kind of brought this in here, but we're going to cut a square out of each corner, okay? And we don't know how much we're going to cut out. We're trying to cut out the best size so that when I make a box, it has the maximum volume. It'll hold the most amount of stuff. So I'm going to call, since it's a square that I'm cutting out, and I don't know how much I'm cutting out, we'll call those pieces X. Right? It's a square, so each of those little pieces is X. So I just want you to kind of see. I know you can kind of see it, but so basically I'm just guessing. All right, maybe I want to cut out 1-inch squares from each corner. Maybe I want to do 1.5 inch. Maybe I want to do 2 inch. I don't know. I got to keep trying until I find the maximum volume. So we're getting ready to do that without guessing. Okay. So I just want you to see. So if you cut out these squares, if they're equal from each side, you guys see that would make a box, right? So I'm going to talk to you about the length and the width and the height. All right. So I cut out my squares. I fold these guys. And I make my box, okay? So you can see the box is a lot shorter than 10 by 18. Okay, so got my box. Hey, it worked, all right. Okay, so that's what we're looking at. So let me ask you this. What would be the height of the box? You just cut out those little pieces. So what would you call the height?
L minus 2.
No, the height, this piece.
X.
That would be X, right? We just cut it, right? That little piece that we cut out. So we agree that the height is X, right? And we're going to figure out the length and the width. Okay, so I know that, so I've got some secondary equations coming up. So I'm going to let the height equal X. So I just want you to see it. So when we folded that piece up, that was the X length. So that's the height of the box. All right, now the whole box says, assume the width is less than or equal to the length. So we'll call this side 10. And then this piece would be the 18. That's the way it looks on our picture. Okay. All right, so let's start with the length. The length is the bigger piece. So the length of our box is not 18, right? We took this piece away, and we took this piece away. Both were X's. So what is our length, which is right here? That would be 18 minus 2x. All right. So there's our length. Okay. And then the width, which is down here actually, we took that x away and that x away from 10 inches. So that would be 10 minus 2x, right? All right, so there's our width. 10 minus 2x. All right, so this problem, even though we always have one main equation, this one had three secondaries. It had a length, a width, and a height. But notice that I labeled all of those with x's. So now I have my height, my length, and my width all in terms of x. So I'm going to substitute. This is that step number 4 up above. We're going to put in all of these secondary equations into the main equation so that we only have one variable. Okay, so we're going to go back to the main. And instead of doing the volume is length times width times height, we're going to substitute in these guys. So the length is 18 minus 2x. Okay, the width, I'm just doing this in order the way we wrote it. So the width would be 10 minus 2x. And then the height was x. Okay? So now you have your volume all in terms of x. So when we do our derivative in a little bit, we don't have to do any implicit. We just take derivatives. But I don't want to take the derivative right now. Okay? That would be kind of a pain to do 3 products. So I'm going to go ahead and multiply all this out and get individual terms so that our derivative part will be easier. All right, so the first thing I'm going to do is just FOIL. Leave that x out there for a minute. So I'm not taking a derivative, I'm just simplifying. All right, so we're just going to FOIL. So 18 times 10, that's 180. I'm going to do the inside and the outside. So outer, negative 36, and inner, negative 20. So that's negative, what did I say, 56. X, and then lastly, negative 2x times negative 2x, positive 4x squared. Okay. Now you could do the derivative now, but I still don't want to do a product rule. So let's go ahead and multiply that x at the back times each of those three terms. So we have 180x minus 56x squared plus 4x cubed. All right. So the whole big part of this problem is really that part. Getting your main equation down to one variable and simplifying it as best you can before you take the derivative, okay? All right, so that was all steps 1 through 4, and now we're getting ready to do step 5. I don't usually number these because they're so different, but I usually always have, our main, our secondary, and then back to the main, and then our work. So that's kind of the way that I do these. I don't like numbering these so much. They're not as specific like it was for related rates. Okay, so we're ready to take the derivative, so v prime. Okay, so derivative of each individual term. So this is not too bad. So 180 minus 56 times 2, 112. 12?
Yeah.
Thank you. My brain is just not working today. And then my dad's been in the hospital, so I've been sleepless for a few days. So, all right, so plus 12x squared. All right, so there's our derivative. We want to maximize. So think about derivatives. Max or min values are where the derivative equals 0. So we're going to set this equal to 0 and solve for x. Okay? So set it equal to 0. All right, and I'm going to rearrange these numbers just so that we have a quadratic. So let's flip them around. So this is 12x squared minus 112x plus 180. Okay? I don't think 12 goes into all that, but we can reduce. 6 doesn't go in. 4? 4 goes into all those, I believe. All right, so if we take out a 4, or divide by 4, however you want to do it, 3x squared, 28, 45. And that won't factor. So we got to do quadratic formula or we got to graph. Okay? So I'm just going to do quadratic formula, solve for x. You could graph it and find the decimals that way. This is going to be irrational numbers. All right, so we've got the opposite of b, so 28 plus or minus square root b squared, so negative 28 squared minus 4 times 3 times 45 all over 2 times 3. Okay, don't need that 4 out front. All right, so that's 28 plus or minus squared. Minus 12 times 45. So square root of 244 over 6. All right, so I'm going to do 28 plus the square root of 244. Get that answer divided by 6. And I'm going to do 28 minus the square root of 244 and then divide that by 6. Okay. So put those over here. Right, so we get 8 plus square root 244, divide that by 6. 7.27. And 2.06. Okay. All right. So there's 2 answers. Now, every one of these problems that you guys are given, the answers that you find, you can kind of figure it out without the calculus part of it. But I want to go through this one with you because I've seen on the final exam, not often, but I've seen on the final exam is after you get your answer, then it wants to know how do you know it's the max. Okay, so we're gonna do it both ways. I don't usually ask you to ever prove it to me on my test, but I have seen it on the final. So if x is, I'm gonna go back. Well, we got this okay? All right, so look back what x was at the top. On your secondary equations, x was the height, right? All right, so if my choices are either 7, a little more than 7, or 2, I want you to just kind of think about that. If you let x be 7, the height, so you cut out 7 inches from each corner, okay? That means the length would be 18 minus 2 times 7. So that would be 18 minus 14. But then look at the width. The width would be 10 minus 2 times 7. So what would happen to the width?
Negative.
It would be negative. So you can't have a box that has a negative length. So automatically I know that 7 can't be the maximum number I'm looking for. So that automatically tells me that 2.06 is going to be my answer, right? So every one of these problems, it's kind of understood what the right answer is. So you really don't have to prove it because all the questions you're given, you're going to get that answer. But I'm going to show you after we do these, finish this, how I know that for sure. So if you're ever asked to prove it, we'll do that in a sec. All right, so I know that my height then is 2.06. Because remember, it asks to find, go back and read the question, make sure you answer the question. Find the length, the width, and the height that results in the maximum volume. Didn't ask you for the volume, just said find the length, the width, and height. All right, so 2.06 is going to be my height. Okay, so I'm just going to plug in 2.06. I don't have room for that. I'm just going to work it out. So 18 minus 2 times 2.06. So the length is going to be 13.88-ish. Don't round so much on web works. So there's the length. And then 10 minus 2 times 2.06, 5.88. Okay? All right, so there's our 3 dimensions that it asks us to find. So usually your answer goes back to the secondary equation. Somewhere back there, you got to plug that answer in and work it out. All right, so that one we kind of knew 7 wasn't even possible just because we're doing lengths. So how do we know for sure? So if on the final exam you are asked to prove, how do you know? You would use the calculus part, which is that you found the derivative right here, and you take that and you do your little number line and find where it's increasing and decreasing. So if I'm looking at this problem in terms of what we did last week, I would take 2.06 and 7.27 as my boundaries. And this is the derivative. So I'm going to plug in my test points into the derivative. Okay. So pick something less than 2. I would pick 1. Pick something between 2 and 7. 5. Pick something bigger than 7. 10. Plug those numbers into either the main derivative or you could plug it into the smaller one down here after we factored out the 4. Okay. So if I plug 1 in, I've got 3 minus 28 plus 45, which is a positive number. If I plug 5 in here, 75. It's going to give me a negative number. You can use your calculator for that. I'm just trying to save some time. And then plug in 10 in here, and that's definitely a positive number. Okay. So the proof is that 2.06 went from increasing, positive, to decreasing, minus. So that's a max. 7.27 on this graph went from decreasing to increasing. So that went down. That's a minimum. Didn't ask me for the minimum. Asked me for the max. Okay, so that's all you have to show to prove that you know that's a max. Okay. And again, I will not ask you to do that on the optimizing problems. You got enough to worry about getting the right answer, but that's how you would check it. Okay, that is the proof, is what we've been doing last week. Okay. All right. So that's the first one. That's probably one of the only ones that has multiple secondary equations. Most of the other ones are not. Okay. Questions? We're okay with those? All right, so let's look at number 5 then. I got those? Okay. All right, so 5 has 2 parts. This was an old exam question. So this is a good one to work on. All right, so we have a cylinder, an oatmeal container. Okay. And it has a capacity of 3,000 cubic centimeters. So what is that? That is the volume, right? Cubic centimeters, so capacity, so we're talking about volume. All right, now they gave you that. They gave you, the thing that they typically give you is the secondary equation, okay? Typically, that's the key to knowing that. All right, so part A says find the dimensions that will minimize the materials needed to construct the container. So we want a formula that's going to minimize the materials needed to construct this container. So what are we talking about when we're constructing something? What is that? The surface area, right? So think about it. You got, your Quaker Oats container, right? So if I'm going to construct it, I got to build whatever they use to make the cylinder part, the round part, which remember is just a rectangle, right? And then we got to put the top and the bottom on it, so those are circles, correct? So that's what we're doing. So that's surface area. So just so you remember, you build something. We'll just call it A for area. All right, so let's think about our container. So we have the top, we have the bottom, and then we have the middle piece, right? All right. So on part B, I know these are the ends. So they call these the ends. So these are the 2 ends. And then on part B, they call this the side. I'm just going to call it what it is in part B because we're going to use it in just a minute. All right, so area. So what's the area of circles?
Pi r squared.
Pi r squared. So this is pi r squared, and this is pi r squared if we're doing surface area. Okay. And don't forget, on your cylinder, this bottom piece is the radius, right? And then this is the height. So what's the area of that rectangle?
2 pi r times
So think about what you're doing. So you've got the height, and then what's the length?
2 pi r.
Right, that's the circumference. 2 pi r?
Pi r squared.
So, right, here's your cylinder. So the height is the length, but then the circumference, this piece, that's your width. So that's 2 pi r. All right, so we got h here, and, oh, no, that's 2 pi r there. I did it backwards, 2 pi r, there's your h. All right, so our area for that is 2 pi r h. Just trying to get everything set up so that I can write my formula. Okay? All right, so the area, our main equation, what we're trying to minimize, okay, would be 2 of these, so 2 pi r squared plus the side part, the rectangle, so 2 pi r h. Whew, okay. So that was kind of the big part of that. So that, to me, those of you that like optimization understand all these, what's the main, what's not, because that's the harder part of it. I don't know, the related rates, almost, it's a little bit easier to figure out the formulas because they kind of give you more information about it. So you just have to kind of think about these a little bit. All right, so now the secondary equation. So think about our main equation first off. I got 2 variables. I've got r's and I've got h's. So if I'm looking at this equation, I would just like to replace the height with something in terms of r so that everything is r's. Remember, pi is just a constant, so it's not a variable. So I'm going to use my volume. So what's the volume of a cylinder?
3,000 equals pi r squared times h.
Okay. Yay, we remembered one. Okay. All right, so the volume for a cylinder is pi r squared h. So we have the volume. They gave you that it was 3,000. So we're going to substitute in 3,000 for V. And then we're just going to solve this for H. Now you could solve it for R, but look at look at this formula and, if I asked you which would be easier to solve for, hopefully you would say H. Because if you're going to solve for R, you're going to get a radical, right? Square root of something, and I don't want that if I don't have to. Besides the fact I've got more R's up here. So let's go ahead and solve for H, because I only have to replace one H, and that's easy. I'm just going to divide. So if I take 3,000 and divide it by pi R squared, R squared, that will give me H, okay? All right, so I took my secondary, solved it for one variable, and now I'm going to replace H in my main equation with what I just did. So just like before, so now I'm going back to my main. Okay. So 2 pi r squared will stay, plus 2 pi r, and instead of H, I'm going to put in 3,000 over pi r squared. And simplify that before you take the derivative. Okay. All right, so if I simplify 2 pi r squared plus, so I'm going to get 2 times 3,000 over here, which is 6,000. The pi's are going to cancel, and that r will cancel with one of the r's in the bottom. So do we agree that we will end up with 6,000 over r? Agree with me, because my head hurts right now. So make sure that's right. All right, and then we're going to take the derivative of that. So we're going to think about this as 6,000 r to the negative 1, right? We're going to do a derivative in a minute. So let's rewrite that as 2 pi r squared plus 6,000 r to the negative 1. Just because we're going to do derivative. I don't want to do a quotient rule. So that's as easy as I can make the derivative. So again, that whole piece is get your main equation down to one variable and as simple as possible. Okay, so from here on out, it's just taking a quick derivative and solving it. Okay, so I'm going to move over to this side. All right, so now we're ready to do A prime. Okay, remember pi is a constant. So the derivative of 2 pi r squared is 4 pi r.
Squared.
And then the derivative of 6,000 r negative 1 would be minus 6,000.
Why wouldn't it just be 4 pi though? Because isn't 4 pi like the, oh, never mind, my bad.
R is your variable.
Yeah.
All right. All right, so this would be 6,000 r to the negative 2, right? So I'm going to put the r squared back in the bottom because I got to solve that. So write it like that. So 4 pi r is the derivative of the first term. This is negative 6,000 r to the negative 2. And I just put r squared back in the bottom. Because now I got to set that equal to 0 and solve it. All right, so if we set it equal to 0, I'm just going to take that negative term and move it over to the other side. Make it positive. Definitely going to run out of room here. So. All right, go ahead and multiply the r squared over to this side. Get rid of your fraction. So that would be 4 pi r cubed equals 6,000. Now be careful in your calculator. We're going to divide both sides by 4 pi, right? So r cubed equals 6,000 divided by, in your calculator, make sure you divide by 4 pi in parentheses. If you don't put parentheses, you're going to get the wrong answer. So r cubed $477, 4648, and then take the cube root of that to get r. Okay, so cube root of 477, 7.8159. We were doing centimeters. Remember what the question asked you to find? Find the dimensions that will minimize. So our dimensions for a cylinder are the radius and the height. So there's your radius, you found that dimension. And then where are you going to find the height from? Go back to the secondary. That's where you always get something. So the secondary equation, you're going to plug in 7.81594 for your radius, square it, multiply it by pi, and then take 3,000 divided by that number. Okay? So your height is 3,000 divided by 7.8159 squared times pi. So make sure you do that correctly in your calculator, and you should end up with 15. Bless you. 631. So there's your height. Okay. All right, so the second piece, I've seen a lot of times these problems where they add crazy little extra things on your final. So I always try to throw these into my notes after the fact. But again, every semester is something different, but I feel like the more I do this, the more problems I can give you guys. All right, so the second part adds money to this, the cost. Okay, so think about it. The first part, we were minimizing the materials. And the materials was just how much of it I needed. Okay? Can I move this? Anybody still good? All right, so look at part B. B says, find the dimensions that give the minimum cost of production of materials if the end materials, so that's the top and the bottom, cost 5 cents per square centimeter to build, and the side materials, that's the rectangle part, the round part, cost 2 cents per square centimeters to build that. So what would I change on this problem to do that? What's going to be my main equation now? The same formula, but how much does it cost to build this? These are the top and the bottom. 5 cents, right? So I'm just going to do 5. You could do 0.05, but we'll just write our answers we're doing dimension, so we can do it either way. So 5 times 2 pi r squared plus, and then how much is it going to cost to build the middle piece? That was 2 cents, so 2 times that. So it's going to change our formulas because now we have the money that it's going to cost. Now, we still have to replace h, but we already did that. You don't have to do it again. What is h? Right? We already did all that. So we already know this is what we're going to end up with right here. Okay? So I'm going to change this to 5 times 2 pi r squared plus 2 times 6,000 r to the negative 1. Because we already did all that work before. We don't need to do that again. Okay? So just grab that from the top. All right, so now you've got 10 pi r squared plus 12,000 r to the negative 1. And now you're just going to take the derivative of that. Forgot that was my error. All right, so you're going to do the same thing. You're going to do the derivative now. This is added in the cost. So we got 20 pi r minus 12,000 r to the negative 2, which I want to put r squared again. So it's going to look very similar to the one we just did. So we're going to set that equal to 0 and solve that. Okay? All right, so if I set it equal to 0, move the fraction part over, make it positive. So 20 pi r equals 12,000 r over r squared. Multiply the r squared over, so now we have 20 pi r cubed equals 12,000. Divide both sides by 20 pi. Make sure you keep that in parentheses. And then take the cube root of that number. So that should give you 5.7588.
Can you pull it back down a bit?
Sure. Is that good? Get it all in there. There you go.
Do we have to?
All right, and then just take that value, R, plug it back in for the secondary equation of H, 3,000 divided by pi, this number squared this time, to get your H value, okay? H squared times pi. And that's about 28. Okay. So you can see your answers are different just based on, what kind of a problem. So anytime you're asked to figure out cost, you're still doing the same formula. You just have to multiply that into whether it's area or perimeter, whatever it is. I've seen it for the fence one, okay, where you're building the fence. Cost for the fence, so you just tack that onto it. Yep.
Where did you get the height formula?
This one?
No, the one at the very end that you used.
Remember at the very beginning, the secondary equation, we took the volume, and we knew the volume was 3,000, so we solved that for H. That's part of that secondary work we did. Got it? Anything else? So I'll leave that up there real quick. All right, so we okay with that one? Good news to me is that most of these derivative ones are pretty straightforward. They're not going to be hard to solve for the letter you're looking for, the variable, but it's all the preliminary stuff you got to get. Okay? All right, so that was a cylinder one. We did the rectangular one. And now we're going back to coordinate planes and using that to help us figure out some problems. So there's all kinds of these. I'm trying to think over the years. Probably the last couple years it's been Farmer Brown and his pen, doing different things with that. But I have seen a distance one. I've not seen one like 6 and 7 that we're getting ready to do in a while. But again, I hate to always say I haven't seen it in a while because then it'll show up. So I just never know. All right, so we good with this one? Still right? Okay. All right, so let's look at number 6 and number 7 are very similar. So once we get through 6, 7, actually I think it's probably easier. Should have probably mixed those, put those in a different order. All right, so number 6. Find the area of the largest rectangle that can be inscribed in a semicircle with a radius of 4 feet. Okay? All right, so the problem here is that we have a circle or a semicircle. So we're talking about the radius, but then we're on this coordinate plane here. So we've got distances of x and y when we talk about it. So that's kind of going to be we got to get this down to one letter. Okay? All right, so here's a semicircle with radius 4. So I don't want to call this the radius because that'll throw us off. So we got a rectangle here, so let's make the radius there. So we can see that we got a little triangle going on there. Okay? All right. Now, if this is a coordinate plane, so if this is 0, 0, and I go over this distance, which is x, and I go up, all right? So there's my x and y. We want to find the area of the largest rectangle. That's our main equation right there. The area of the largest rectangle that we can fit inside this semicircle. All right. So, do we agree because area of a rectangle, that's easy, length times width, right? Base times height, however you want to. So look at that picture and tell me what is the length.
Of that whole rectangle.
Yep,
2x times y.
because this is the rectangle that we're putting in the circle, right? Right there.
2x times y.
All right, so we see that the length is not just x, it's 2x, right? So we have the area is 2x times, what's the width of this rectangle?
Y.
Y. All right, so would that make sense then, what I wrote down? So length, 2x, and the width is y. Now, question says, find the area of the largest rectangle. So your answer to me when we're done is not what the length and the width equal, but it's the area of that. So when you solve for x, that's not the length of this rectangle, right? So you got to just keep a lot of this stuff in mind as we go through. All right, so what would be the secondary equation? I need something to solve for y with.
X times y over 2.
Look at those three things right there. That's a triangle.
X times y over 2.
What am I saying? What?
X times y over 2. Base times height divided by 2.
No, but I need all this stuff. So this is so let's try a Pythagorean theorem, okay? All right, so let's do x squared plus y squared equals what?
R squared.
Not r squared.
Oh, 16, okay.
Yeah, 4 squared, right? Radius is 4. Should we put that in there? There we go. Radius is 4, they gave you that. Remember, your secondary equation, they're always going to give you something about it. So they gave you that the radius was 4. That's always the piece of the secondary equation. All right, so that would be 4 squared, which is 16. So I want to solve this for y so that I can get my main equation down to one variable. All right, so y squared equals 16 minus x squared. And this is my favorite part. If you take the square root, what do you get? Please don't tell me you get 4 minus x. Right?
Square root of 6.
You get the square root of 16. You can't do that. You take the square root of this. That is not 4 minus x. Okay? You cannot break apart numbers under a radical. Very common mistake. Okay, so now our main equation, I'm going to put it back up here so I have some room. So now, our main equation, I'm going to substitute this y for what I have. So the area is 2x times the square root of 16 minus x squared. All right, and I can't really simplify that. I mean, that's a product. I got to do a product rule. Can't multiply a number times a radical. All right, so we're ready to do our derivative and then set that derivative equal to 0. So let's do a prime. All right, so 2x is your first function, and then remember the square root is 16 minus x squared. That's to the 1/2 power, right? All right, so we're going to start with the derivative of the first, 2, times the second, leave it alone, plus first, okay, times the derivative of the second. All right, so that's 1/2, 16 minus x squared to the negative 1/2, times the derivative of the inside,
Which is negative 2x.
negative 2x. All right, so we want to simplify that before we set it equal to 0. All right, so the first piece, 2 times square root of 16 minus x squared. All right, let's talk about what's in the top and what's in the bottom. So just looking at this, I know the square root is in the bottom, right? This 2 will cancel with that 2, so get rid of those. So you have an x in the numerator, and then you have this negative 2x. Okay, so what do we have in the numerator? 2x squared over that square root in the bottom. Let's make it minus. You could put plus and put the negative in the top. So it looks kind of nasty, but remember, since we've got the same radicals, they're going to go away in a minute, so it'll work out nicely. All right, so we're going to set this equal to 0. Go ahead and move that negative, that fraction over to the other side, so we get rid of that minus sign. And then we're just going to cross multiply, so we'll get rid of that radical in a minute. Okay? All right, so we're going to multiply the square root of 16 minus x squared over here, so those radicals are going to go away. So that's 2 times 16 minus x squared equals 2x squared. And then we just got to solve that. So let's distribute. So 2 times 16, 2 times x squared. Since I don't have a middle term, I'm going to go ahead and move the negative 2x squared over to this side. So that's 4x squared. Divide both sides by 4. So x squared is 8. So x is the square root of 8. And you can, I'm just going to leave it square root of 8. You can write the decimal, but. All right, so now I can answer the question. Find the area with the largest rectangle. Find the area of the largest rectangle. So I'm going to, first off, I got to find y, because remember the area formula is 2 times x times y. So that's what I'm getting ready to do, so I need to know what y is. So to find y, I'm going to put the square root of 8 in here. Okay, so let's find y. Square root of 16 minus square root of 8 squared. Okay. So the square root of 8 squared is just 8, and 16 minus 8 is 8. So y is also the square root of 8. Make sure you see that. Okay, so the square root of 8 squared is 8, and 16 minus 8 is 8. So y is also the square root of 8. So now I can find the area, which is 2 times x times y. So 2 times the square root of 8 times the square root of 8. Square root of 8 times square root of 8 is 8. Times 2 is 16. And that would be feet, square feet. Okay. All right. Good with that one? Now, I'm going to kind of skip over 7. I'm going to start it, but I'm not going to finish it because it's very similar to what we just did, and I want to make sure I get to the other ones. But let's just kind of, because I'll show you why it's a little bit easier. They actually give you, this is the secondary equation right here, so you don't have to figure anything out. Okay? So number 7 says, find the dimensions of the rectangle of largest area. So again, just did that. That has its base on the x-axis and the other 2 vertices above the x-axis lying on this parabola. Okay? So you're still going to have the same area, which is 2xy. Because this is your x, this is your y. You're still doing that rectangle. But this time your secondary is right here. So all you're going to do is substitute in for y, 4 minus x squared. So it's actually a little bit easier. You don't have all those radicals and all that. Okay? And then you'll do it the same way. So your secondary is already here. I gave you that. Y equals 4 minus x squared. And then you'll substitute that into the main. So 2x times, like that. And then you just distribute. I would distribute, get individual terms, and then you'll do your derivative. So that one's much easier, I think. Okay? All right, so I don't want to do 2 of those. I'd rather do a different type. We good from there? So distribute that, and then take the derivative after you distribute. Okay? All right, so let's look at something a little bit different, because number 8 I've seen a couple times recently on finals, so I want to make sure we're okay with that. Okay. All right, so let's look at number 8. Find the point on the line y equals the square root of x plus 1, which is closest to the point 3, 1. Closest, okay? So there's, again, that's an optimization process. Doesn't really tell you that. So we are looking for a point, an ordered pair, x comma y, that's on this curve, closest to the point 3, 1. So this one doesn't have a picture, so let's kind of look at what that means. So if I have this graph, square root of x plus 1, that means that's the square root curve, which is, right, that little half curve, but we got to go left 1. So it starts over here at negative 1, 0, and it kind of goes like that. I'm just sketching. I don't have the exact numbers on there. And then I look at the point 3, 1. And here's 3, 1. Then in geometry, we learned that the point that's closest to another point, that's perpendicular to it. So if I sort of draw a line perpendicular, okay, that's what I'm looking for. What is that point? Closest to point 3, 1. Okay. All right, so when we're talking about how far away something is from one another, that's a distance. So we need the distance formula. That is our main equation. Okay? So I'm going to write the distance formula up here because I don't want it as part of my work, but let's just remember distance formula. So x2 minus x1 squared plus y2 minus y1 squared. So we're going to substitute in our values that we have. So one of our points is 3, 1, and our other point is xy. That's what we are looking for. Okay, so we're going to substitute that in. That will be our main equation. All right, so main equation, distance. So we're going to subtract the x's. So let's do x minus 3 squared. Plus, and then subtract your y's, so y minus 1 squared. All right, what's our secondary equation? They always give you that. Something about it. So your secondary is right there, y equals the square root of x plus 1. So now I can take my main equation, get rid of this y by substituting in what y is equal to, and then everything's in terms of x. That's what I want. I have to have down to one variable. All right, it's going to look nasty, but we can do it. All right, so we got x minus 3 squared plus, and then in place of this y, we're going to put what y is. So the square root of x plus 1 minus 1 squared. I got to stop writing so big. It's way too big. All right. So, let's go ahead and simplify what's under the radical first, I think. I don't want to take the derivative yet. Okay, so let's go ahead and square those parentheses. Let's see what happens. Okay, first one's easy. All right, so we're going to square x minus 3. So that would be x squared minus 6x plus 9. Okay. All right, this one's not as bad as it looks. All right, so we're going to square this, so just so you can see it. So we're doing this. No, we're not. So, slow down. All right, so we're getting ready to do this, so I just want you to see it. So we're doing square root of x plus 1 times the square root of x plus 1. So we're doing first, which is easy. That's the x plus 1, right? So that goes away. Now, what's the outer? That would be negative square root of x plus 1, and the inner, negative 1 square root of x. So inside we get minus 2 square roots of x plus 1. So that's the outer and the inner. And then we're going to multiply negative 1 times negative 1 plus 1. All right, so let's simplify that down. We got a bunch of like terms in there. Bless you. All right, so I got x squared. I've got minus 6x and a positive x, so that's minus 5x. I got 9 plus 1 plus 1, 11. And then that. That's what I'm going to take the derivative of. Okay. Nice things happen with this one. And it'll always happen with distance. We'll talk about, we already actually did this, well, it was a while ago, so I'm not going to pretend that you guys remember this, so we'll just go through it. All right, so let's do the derivative. Okay, so d prime. So 1/2 of all this to the negative 1/2 power, right? Okay, so that's how we'll start. And then times the derivative of the inside, right? So you ready to do that? All right, so now we're just doing the derivative of the inside. So that's 2x minus 5. And then we got to do the derivative of this. So I'm going to leave the 2. That's constant. And then the derivative of the square root of x plus 1 is 1/2 x plus 1 to the negative 1/2 times 1, which we don't need. Now, that looks nasty, but remember what that whole first piece is. It's in the bottom. And what happens when you set a fraction equal to 0, when you multiply the bottom over, it goes away, right? So I'm going to write it, but we don't really need it. So this is in the top. I'm going to put this in the bottom. So I've got 2x minus 5 minus, and I'm going to go ahead, simplify this. 2's are going to cancel. So this is 1 over square root of x plus 1. And then all of this stuff's in the bottom. Okay? So I just want you to remember what happens with all that. When you set that equal to 0, that goes away, right? You're going to multiply this over there, so that is gone. So every distance problem you ever have, what do you really need? Think about it. Once you do the derivative of that big square root, all you need is the derivative of the inside, or the underneath the radical, because that whole first part is going away. So every one of these distance problems that you work with, and after you do about 3, 4, 5, 6 of them, you'll see that. So I'm just trying to bump you ahead there, okay? So when you do the derivative of the main thing, that's all going to be in the denominator, and it's all going away. The only thing that stays in the numerator would be the derivative of the inside. And so that's really all you have to ever do on these. But, doesn't hurt to do it just to make sure. So all we really will have set equal to 0 is this, and that's what we have to solve. And I would solve that by graphing it. I'm not going to do that by hand, okay? So this is going away because I'm multiplying it over to this side. And I want to solve 2x minus 5 minus 1 over the square root of x plus 1. So I'm not doing that one by hand. I wouldn't expect you would either. So we would graph that and find its roots that way. Okay? So if I graph it, I'm just going to put graphing. I will get x equals, I'm just trying to save a little time here, 2.76. Okay? Bless you. Square crosses the x-axis. Okay, solving that. So if x is 2.76, because I graphed it, where am I going to find y? Remember that secondary equation up here? So you're going to plug in 2.76 plus 1, so that's 3.76. Take the square root of that. So y equals Okay. 3 square root of 3.76, which is 1.9-ish. So that's an ordered pair. Okay, so look at our picture. Does that make sense? That the point closest to 3,1 is about a little bit less than 3, a little bit less than 2. Look at my dot on my paper. So I went a little bit close to, between 2 and 3, and then I went up. So that seems right. So just kind of eyeballing. I feel like we did the right thing. So there's our ordered pair. That is the point closest to the point 3,1. Okay. All right. That was kind of the worst one, I think, on this whole page, because that distance is nasty. You have one of these on WebWorks, so just kind of follow along this and just kind of remember what I told you at the end when you're doing your derivative. So yours will be very similar to this, other than your point's probably different. Okay. Okay, so let's set up and do, this last one's pretty quick, so let's go ahead and do this one. It's an easy derivative to take. So let's get that done. And then I want to just remind you, at the bottom, sorry, on the next page, because I don't do these with you, but 10 through 12, those solutions are on Canvas. You have a problem in WebWorks, so these are kind of long and monotonous. So what I decided to do was just put these on Canvas, and that way you could follow along with it and put your numbers in there. I don't ask you these on our test, so they're just to get you through the WebWorks. So follow that one if as you work on those, and then you should be okay with getting your answer. So that's 10, 11, and 12. Those are on Canvas. And if they're not, they'll be open soon. I think I already opened them, but. All right, so let's look at number 9 real quick. So we have a 2,000 square centimeter, we have 2,000 square centimeters of material, and we're going to make a box with a square base and an open top. So again, surface area. Okay, we want the largest possible volume. So that's our main equation. So your main equation is the volume. So again, we started with this, length times width times height. Okay, so our secondary is the surface area. Okay, so we have 2,000 square centimeters to make this box that has a square base. So let's talk about, I'm going to label length, width, and height. Okay, length, width, and height. I need one variable. So first off, if I have a square base, I can make both of these the same. So I'm going to get rid of the W and call it L, because the length and the width would be the same. It says it's a square bottom. Okay. All right. And I have surface area. I'm building the box. So the surface area is 2,000. And that equals the formula for surface area. Okay, so let's start with the area of the base. How would I find the area of the bottom? L times L, right? Which is L squared. Plus, how many sides do I have on this box? 4 sides. And what is each side? What is the area of one of those rectangles? H times L, right? You guys see that? So this one is L times H. Yes?
What did you do? 2L squared? Because you have 2.
Nope, because it has an open top. But if it didn't say open top, yes, it would be 2. But since I'm not doing the top, it's open, so I don't have to construct it. So that's why it's just one of those bottoms, okay? That's a good question. All right, so do we see that we have 4 sides of this box that are all L times H? L times H, so 4 L times H. So 4 LH. All right. So I want to solve this for H, okay? So that's not hard to do. So solve this for H. So I'm going to do 2,000 minus L squared equals 4LH. And then I'm going to divide by 4L. Okay? Now, let's go ahead and divide it individually. So 2,000 divided by 4L, that's 500 over L, which is 500 L to the negative 1. Let's go ahead and, so I'm going to divide each of these terms by 4L. So 2,000 divided by 4 is 500 over L, but I just wrote it out because I'm going to take the derivative in a minute. So write it as L to the negative 1. And then minus L squared divided by 4L would be 1/4 L, right? Or L over 4, however you want to write it. All right. So we'll finish this up next time, but you guys can now continue, and then we'll see what you get. But remember, so now you're going to replace, W is already L, so you have L times L times, and then this is your H. So you're going to have everything in terms of L, okay? So we'll pick that up next time and finish it. All right, so we can stop recording. I just wanted to go through and finish this up. I told you guys to try that one on your own. This number 9 from section 4.5. Okay. All right, so just a reminder, we were looking at a box and we were trying to find the largest possible volume of this box. And this is a box that we were creating that had an open top, so no lid on it. Okay, so our main equation was the volume, which is length times width times height. They told us that the bottom was a square, so I replaced W with an L. Remember, we're trying to get this down to one variable. And then the height we were going to get from the secondary equation, which was how many square centimeters of material it took to construct this box, which is surface area. So the surface area, which is 2,000, that's what they gave you. The area of the bottom, which is L squared, and then the area of the 4 sides of the box. So remember we talked about each side of the box was L times H, and we had 4 of those. All right, so we took this equation and we solved it down for H. Okay, so that's where we ended up. So now I'm going to take the main equation and write it all in terms of L. Okay. All right, so we have L, which is the length, times, and instead of W, I'm going to put in L, because that was the box down there, or the square. And then times H, which I'm now going to use this 500 L to the negative 1 minus 1/4 L. So now everything is in terms of L. And I'm going to simplify this before I take the derivative. Okay. All right, so first off, the L times L, let's go ahead and write that L squared, just so you. Okay. And then I'm just going to distribute. All right, so remember when you're multiplying, you add exponents. So we got L squared times 500 L to the negative 1. So that would be 500 L. And then L squared times negative 1/4 L would be negative 1/4 L cubed. Okay, so there's your volume, written all in terms of L. So you can take the derivative of that, set it equal to 0, solve. And remember what we're asked this time. This time it asked you to find the largest possible volume. So not only do you have to find what the length and the width and the height equal, but then you got to multiply those 3 things together and give the answer as the volume. So these questions, you've got to always be careful that you're answering what they ask. The other one we did just asked you for the dimensions, okay? All right, so we're going to do the derivative. So V prime. So 500 is the derivative of 500L. And then minus 3 times 1/4, 3/4 L squared. And you're going to set that equal to 0. And we're going to solve that. Okay, so I would move the 3/4 L squared over to the right. Make it positive. All right, multiply both sides by 4/3 to get rid of the 3/4. So if we multiply 500 times 4/3, that's 2,000 thirds. I just leave it that way for a minute. So 2,000 over 3 equals L squared, then just take the square root of that. So we get 25.82. So these are in centimeters. Okay. So there's the length. The width would also be 25.82, right? They were the same. And we need the height. So we would put that in here, but I'm going to rewrite that. It's kind of hard to do it that way. So let's rewrite the height. Okay, so we have the length, we have the width, and then we need the height. So the height up here, let's write it as 500 over L minus 1/4 L. That might make a little more sense. And then you're going to replace these L's with 25.82 and figure out what H is equal to. Oop. Stay up there, paper. Okay, so 500 divided by 25.82 minus 0.25 times 25.82 should give you 12.91. All right, so there's your 3 dimensions. So then find the volume. We're just going to multiply those 3 numbers together. So 25.82 times 25.82 times 12.91. So 8606.63. And that'll be cubic centimeters. Okay. All right. And again, typically on the exam, they'll give you volume formulas, probably surface area formulas, maybe. Can't always depend on that. You won't get distance formula. You won't get, the formulas you should know that they won't give you. So kind of like we did with related rates, okay?